Right, welcome back. In this activity, we're going to draw the AC generator. Now, you're going to draw it too, along with me. We're going to draw a series of diagrams to explain how this thing works. Now, I really wish I had a pause function, but I don't. So I'm just going to have to do it as we go along. No cheating. Okay, you could do this on a blank sheet of paper and stick it into your lab book, or you could do it directly into the lab book on the lined pages. Either is okay. If you're not ready to go, pause now and sort yourself out. So, we'll make our title Drawing the AC Generator. Now, the first diagram that we'll draw is the general arrangement of the generator. And so I think the easiest way to do this is to start with the axis through the middle. Okay, I'm going to go here. And I'm going to do this in red. Okay, now around that axis we're going to draw the coil. So go from here, I'll go from here. Okay, so that's one side of the coil, and then this is the front end, and this is going to be the output. And on the other side, we're going to have the other output. And there's the other side of the coil. And that's not too bad. So that's the coil lying flat. Now, so this is the axis, or actually it would have to be the axle, because the coil would have to be mounted on an axle which allows it to turn, and we have some external force which causes it to rotate, like so. Okay, now if we spin this coil, I'm going to label it as a coil. Yes, I'm going to label it as a coil. So, if we spin this coil, nothing's going to happen. But if we spin it in a magnetic field, then we'll generate an EMF. So we need to put in the field. I'm going to put it in over here. This is the bit I find hard. Okay. Okay, not quite sure about the perspective, but that is supposed to be the a permanent magnet, and this is the North Pole face of it. So actually it would be a plain pole magnet, one of those dark ceramic magnets that we have. Now we need to have another one on the other side, so I'm going to put it here. This, of course, is where art meets science. I guess other teachers wouldn't do it this way, but then I'm not like other teachers. Okay, so permanent magnet, another permanent magnet, North Pole, South Pole. Okay, so if we spin this coil in the field between these magnets, that will generate an EMF, as we explained a little bit earlier. The EMF is no good unless we can actually draw off a current. So that's where the slip rings come in. So we need to draw two slip rings. The slip rings are centered on the slip rings are centered on the axis because they have to spin around it, but one has to be connected to one side, something like that. And the other one has to be connected to the other side. Not quite sure if I'm getting that right. Now, fortunately, the operation of the slip rings and the brushes is a little bit outside our spec. In practice, the brushes are little carbon brushes, little contacts made of carbon, and they have little springs to push them against the slip ring to make a good connection. So there's one, and the other one would be round about here, something like this. So we'll label those as brushes, and these are slip rings. Okay, I'm going to label the permanent magnets too. That's basically it. Coil, permanent magnets, slip rings and brushes. Okay, now that's the hard part over, you'll be glad to hear. After this it gets a bit easier. If you need to pause at this point to get your diagram sorted out, do so. Now, what we'll do now is we'll go schematic, and we'll draw a series of diagrams, I think, across the page. I'm just going to make myself a little construction line here. So let's start by drawing our coil viewed edge on, in other words, looking along the axis. And we'll start by drawing it vertical, I think. Okay, so if we were looking at the coil edge on, it would look something like that. Remember, what it looks like is pretty much the coil in the simple motor, which is a rectangular coil wound onto a sort of rectangular blue armature. So if you looked at it edge on, what you'd see is there's the axle going through the middle, and you'd see the coils, or the turns on the coil, like that. Okay, and the whole thing is going to turn clockwise, like that, due to an external force. Now we have the permanent magnet, or the magnetic field, each side, and it's going to look something like this. Okay, I'm going to reproduce roughly what the book does. So in a real motor, the permanent magnets have slightly curved faces. So this would be the North Pole face, and this would be the other magnet, and it would be a South Pole facing outwards. Now, I think I'll use color to represent the field, and I'm going to use pink because that's what the book does. Okay, so the field lines, what we basically have is a uniform field in between the magnets. That looks something like this. Okay. The construction in the middle here, and yeah, okay. Now, after a quarter turn, our coil is going to have moved round to this position, and it will then look like this. So if it started out in the vertical position, it's moved through 90 degrees to get to here. After another quarter turn, it will be vertical again. And look like that. So it's now moved from here to here. And after a further quarter turn, it will be horizontal. So it's now gone from here to here. Now, a clever teacher would have space for a fifth diagram. The less clever teacher will squeeze it in. So after one more turn, or one more quarter turn, all right, I think so. No, it's not. How did it get to there? Oh yes. So actually, it's going from here back to here. Okay. So it's moved 90, 90, 90, 90, so that's 360 degrees altogether. Now, we don't need to draw in the magnetic field at each stage because we know that it's there. Or at least we don't need to draw the magnets, but we will draw the field lines. So we have a field line here, 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 and here. Here, 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 here. Here, 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 and here. Now the field, of course, doesn't change. It's constant in magnitude and in direction. Okay. Now, let's look at what's happening here. And we can explain what's going on, and then we'll try to apply some mathematics to it. Yeah, actually we'll do the graph first. Okay, so when the coil is in the starting position here and vertical, the magnetic field is perpendicular to the coil. So there is maximum magnetic flux linkage. After 1/4 of a turn, the coil is now parallel to the field and the flux linkage is 0. After another 1/4 turn, so the coil is going like that, then like that, and then like that. The coil is vertical again and the flux linkage is maximum. Another 1/4 of a turn, flux linkage is 0, and another 1/4 turn returns it to its starting position and the flux linkage is maximum again. So we'll actually draw a little graph next. So this is going to be an axis representing the angular position, theta, of the coil, and on the vertical axis we want to represent the flux linkage, n phi. Okay, now let's see. As we go across, that's going to go from 0 to 360. So, yes, I've got about 20 centimeters there, so I want to break that into 4 times 90, which is 5 each. Let's move this just a little bit that way. Say 5, we'll say 4.5. So 1, 2, 3, 1, 2, 3, 4. Okay. So this is going to be 0 degrees. I'm putting in the degrees just to get myself right. 90 degrees, 180 degrees, 270 degrees, 360 degrees. Okay. All right. Now, this is the 0 degree position, and when it's in the 0 degree position, the flux linkage is maximum. So it's got to be up here. So let's just put a little construction line in to represent maximum. So the flux linkage is up here. Okay, so that's in this position. Okay, now 90 degrees later we're here, and the flux linkage is then 0. 90 degrees later we're at 180 degrees. The flux linkage is now maximum, but the coil has turned around and is pointing in the opposite direction. So although the flux linkage is maximum, we have to indicate it as negative. That might freak you out. I know it's freaking me out. There. Okay. At 270 degrees, we're horizontal again, and flux linkage is back to 0. And at 360 degrees, we're back to the starting position. Flux linkage is maximum and positive. Okay, so 19 minutes. Okay. Now, we have to infer a little bit, but if you had to guess, what would you say the shape of the graph that we're going to draw is? Is it going to be a zigzag? Is it just going to go down like that and then up like that? No, you're quite right. It isn't. It's going to be sinusoidal. Now, we'll have to justify that, but we will infer it for now. Okay, I'm going to have to turn sideways to draw my sine graph. So what we're going to get is something like this. Okay, so this is showing n phi, which is the flux linkage in the generator against angular position theta. Now, yes, okay, so that's here, that's here, that's here, here, and here. Now, the clever bit is going to be, can we deduce the EMF from that? So we're going to draw another little graph underneath. I'm going to push it a little bit. I think I do. Okay. So this is E, which is the induced EMF. And this is our angular position theta. And we're going to use the same scale as before. So this is 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. And this is the EMF. Now, I'm going to put a construction line for a maximum EMF, and yes, there's going to be a maximum and negative EMF as well. Now, if you remember Faraday's law says that the magnitude of the induced EMF is equal to the rate of change of flux linkage. Okay, the rate of change of flux linkage. Now, this is showing flux linkage, and flux linkage is changing with angular position. But the angular position changes with time. So when we plot the angular position, we're really plotting time. It's proportional to time because the coil is rotating at a constant angular velocity. So we can think of theta as being time, and therefore, if we plot if we want to find the rate of change of flux linkage with time, that is going to be the gradient of this graph. Now, if we plot gradient, I think I'll change color to this and do it in green. When theta is equal to 0, the gradient is 0. Therefore, the rate of change of flux linkage with time is 0. Therefore, the EMF is 0. Now, where else is the rate of change? No, let's work our way through. At 90 degrees, the rate of change of flux linkage is maximum, because the slope of the graph is maximum. Now, it's maximum and it's negative. So the induced EMF will be maximum then. But we have to include Lenz's law as well. And Lenz's law says that the induced current, and therefore the induced EMF, is opposite in direction to the change in flux linkage that produced it. So if we have a negative rate of change of flux linkage, we have to represent that as a positive EMF. So we're going to plot up here and not down there. Okay, at 180 degrees, the gradient is 0. Therefore, the EMF is 0. At 270 degrees, the gradient is maximum and now positive. Therefore, the EMF is maximum and negative. And at 360 degrees, the gradient is 0, and therefore the EMF is 0 again. So EMF goes up, goes down, goes negative, goes 0. What shape is the graph? Yes, it is sinusoidal. So we can draw it like that. Like that. We've missed the point. Like that. And finally, upside down, I know, like that. Good afternoon, Mr. Bosco. Okay, now you can't quite see the end of that graph. There it is. Right, so the induced EMF starts at 0 when the coil is vertical, reaches a maximum, goes back to 0, reaches a negative maximum, and goes back to 0. Okay, now you might want to pause to get those graphs to work out. And then we're going to try to calculate or work out what the equation that is governing this actually is. Okay, now I don't get that luxury. I have to keep going because we're going to finish this in 2 videos. 26 minutes. Okay, we're going to go a little bit over half an hour. Call it value added. Okay. I think we can do this. All right. I'm going to do it in pencil because it makes me feel better. Okay, if we start here in position 1, the 0 degree position, what we want to work out is, first of all, what is the is that how we want to do it? Yes, it is, actually. Where is it? Yes, it is. We'll do it that way. Okay. So, in this first position, we can say that the coil is perpendicular to the field. If we want to work out if the magnetic flux density is B and the area of the coil is A, and by the area we mean the rectangular area, which is this area here, which would be length times breadth, that would be the area. The coil has area A, and if it has N turns on it, then the flux passing through the coil would be B times A, and the flux linkage, N phi, would be B times A times N. So, I'm going to put that underneath here, I think. So, when theta equals 0 degrees, the flux through the coil, phi, is going to be B times A. The flux, the linkage, N phi, is going to be B times A times N. Okay. Now, we know that when the coil moves through 90 degrees, the flux linkage goes to 0. Okay. But what we'd like to know is what is it doing in between? What is it doing at some general position? So, to do that, we have to draw one more little diagram, which is here's the field. Now, there's the vertical position, but if the coil has actually moved through some angle and is now here, Now we need to be careful about the way we represent this angle. Okay. So if you remember from magnetic flux, we don't measure an angle from the plane of the coil or the area under consideration. What we do is we draw a normal to the coil, like so. So that's a normal. And then we measure the angle from the normal to the magnetic field vector. So there's the magnetic field vector, there's the normal, and if we measure this angle, that's our theta. Okay. So when the coil was vertical, theta was 0. If the coil is moved away a little bit from the vertical, it's now some intermediate angle, theta. If it moves through a full 90 degrees, the normal will now be pointing straight down, and the angle between the normal and the field will be 90. So this is the general case when the angle is some angle theta. Okay, so in that case, we can resolve the magnetic flux vector through the angle theta, and the component of the field which passes through the coil is going to be B cos theta. Okay, so at some angle theta, the flux density linking the coil is B cos theta. Then the flux phi is B times A cos theta, which is the same thing as B cos theta times A. The flux linking the coil, N phi, is equal to B cos theta times A times N, which is going to be B A N cos theta. Okay. Yes, that's okay. Yes. Okay. Now, theta is the angular position of the coil. But the coil rotates. At a constant angular velocity, or angular speed, as I think we prefer to call it, of omega. Therefore, its angular position theta at any time t is equal to its angular speed omega times t. So therefore, our flux linkage is B A N cosine omega t. Right. So that gives us an expression for the flux linkage as a function of time. Now, hang on, we're nearly there. You want to go out, Mr. Bosco? I can't pause. All right. Okay. Well, do you remember earlier that we said that we noted that E was equal to minus delta n-phi over delta t. That's the combination, of Faraday's law and Lenz's law. So we're going to use that here. So we have that E, the induced EMF, is equal to negative delta n-phi over delta t. Now, delta n-phi by delta t is, well, delta n-phi is the change in n-phi with respect to time. And if we have a change in n-phi over a change in t, that will be an average rate of change and therefore an average EMF. If we want the instantaneous EMF, then we need to resort to calculus and say that E is equal to minus d of n-phi by dt. In other words, we want to find the negative of the differential of n-phi with respect to dt. Now, we know we have a function for n-phi, it's BAN cos omega t. So, if we put those two together, we want to find d by dt of BAN cosine omega t. Now, if you're not A-level maths, don't panic. Okay, can we differentiate this function with respect to time? Yes, we can. It's a function of a function. It's a cosine function of a simple multiple. Okay, now B is constant, A is constant, and N is constant. Same field, same coil. So they're just constants and they just come out as constants. What is the differential of cos? That's right, it's negative sign, I think. So we have a negative sign out the front. We have B, A, M, which are constants. The differential of cos is sine. No, it's negative sine, I think. Yes, it is. And omega t differentiated with respect to t. So that's and the differential of the function within the omega t is just omega. So we're going to get that. Now, if we sort that lot out, we have a negative and a negative, so they cancel. We have B, A, and M. A factor of omega has appeared, and it's constant because the coil is rotating at a constant angular velocity. And we have sine omega t. Okay, so what we've done is we've shown that the EMF is equal to B, A, N, omega, sine omega t. Now, we learn that the Greek letter omega is pronounced U. So therefore, E is equal to ban U sine ut. Ban U sine ut. Okay, so we've derived the equation for E. Now if we compare that back to our graph, can you see that? Yep. The graph of EMF against theta, which is effectively time, is a sinusoidal graph, we guessed. And our function tells us that EMF is basically a big constant times the sine of omega t. So it's a sinusoidal graph. Okay. So what we deduced earlier agrees with what we have here. Right. Now, for our purposes at A level, what do we actually need to take from this? We need to be familiar with the basic construction of the AC generator. Okay, so that is a coil of wire spinning on an axis due to an external force between two permanent magnets. We need to at least be aware that the induced current is extracted using a slip ring and brush arrangement. We definitely need to know how the EMF is produced. So this idea of the coil moving between the magnets and catching an amount of flux, or linking an amount of flux in the coil, and that goes from maximum to minimum to maximum to minimum to maximum. Therefore the flux linkage changes in this sort of a way, and then we need to use Lenz's law and Faraday's law to deduce that the EMF varies sinusoidally like this, okay, between 0 and a maximum and a negative maximum. Right. The derivation for the general case we don't actually need to be able to reproduce. We do, however, have to be able to know and use this equation, E equals BAN omega sine omega t. Okay, so that gives us the EMF induced at any time t. Incidentally, we should take one more thing out of that, which is that's E at any time t, but if we wanted to calculate the maximum EMF, which we could denote as E0, E0 will occur when the sine function maximizes, which is to say at some value of t it will take a value of 1, and then the maximum EMF will be just BAN omega, or BANU. Okay, and we need to know that as well. Right, that was a quick review. Let's review the review. Okay, so we're aiming for how does a simple AC generator work and this equation. Right, we've reviewed what we knew about magnetic flux, flux linkage, and electromagnetic induction so far, in particular Faraday's and Lenz's law, which you should now know in words. We've looked at the construction and the operation of the simple alternating generator. Unfortunately, we can't look at the real thing, but these are the breaks. We've drawn some diagrams of the generator's construction, and we've also drawn some little diagrams to show how it operates. We've deduced the graph of E against t, and we've derived the equation E equals BAN omega sine omega t. Okay, that is pretty much what the book does and what your specification requires. What would be nice is now to apply that to some examples, but we'll do that in the next lesson. So we're just coming up on 45 minutes in this video. The previous one was just under 30 minutes, so we've gone a bit over the hour, but altogether that's not too bad. Okay, these notes, well, I'm hoping that you will have produced your own version of all the notes that we've made today, because that's how you learn this stuff. If you really wanted, I could upload the notes to you, but so you can let me know if there's any points that you don't like and you would like me to do that. This stuff is quite conceptual, so you have to work through the concepts, but once they're well, you've got them, you kind of got your head around them. Actually using them is fairly straightforward. Okay. Hope you enjoy the rest of your day. Don't forget to get outside for your one excursion for exercise. I think I'm going to go and get a little bit of fresh air. Now, to get over all of that. Right. Okay. The end. Good afternoon.